Okay, so in this next tutorial, we're gonna actually remove the walls of the maze, of the cells, to make it, look nice. So let's make a new function here. If you haven't watched any of the previous tutorials, then you go do that now, because obviously you won't understand any of this without the previous ones. So we pass in A and B, current and next cell. Yep. So local x is equal to A dot x. Take away B dot x. If x is greater, obviously equal to 1, then A dot walls 1 equals false, and B dot walls 4 equals. I'll explain this in a second. Else if x is equal to -1, then basically the opposite. A dot walls 4 is equal to false. B dot walls 2 is equal to false. Okay, so what we're doing here is in the walls array, which we made up here. Let me try to find it. See, it's made up of 4 bool values. So front, left, back, right. So if it's equal to 1, then the front one's gonna go. Oh, wait, is that right? Oh, sorry, this is meant to be 2, isn't it? Yeah, no, this is meant to be 2. If x is equal to 1, the A wall's left wall needs to go, and the B wall's right wall needs to go. If it's the opposite, the right wall needs to go, the left wall needs to go. So we just need to write this out for the y as well. So let's copy this whole thing actually. Zoom in a bit. Local y is equal to A dot y. Take away B dot y. If y is equal to 1, then this will be 1 and 3. That'll be 3 and 1. And we're setting them to false still, because we're making them invisible. And then okay, we need to loop through them and make it so you can't collide with them. So let's just do a simple loop here. A dot walls. Do if I is equal to 1. Okay, so it's kind of annoying to write out, but if I is equal to 1 and V is equal to false. So if it's meant to be invisible, A dot W dot can collide equals false. A dot W dot transparency equals 1. So we're basically making it invisible. Else if I'm going to copy this. If it's equal to 2 and V is equal to false, then it's going to be A instead of W. And we only need to do this 2 more times. If it's equal to 3 and 4, that'll be W, A, S, D. I believe that's it. Yep, okay. And just copy and paste this. Do the exact same thing for B. So B dot W, A, S, D. And that should make the walls go invisible and make it so you can walk through them. I've purposely put my walls really low down just so it's easier to see in the video, but you can make yours higher, like it would be in a real maze. So let's see what happens when we run this. Hopefully no errors. Oh, there's an error here. Attempt to index function with base 57. Oh yeah, okay. It's meant to be next cell. Next cell dot base dot color. Let's run this. Okay, as you can see, it's actually working here. Well, almost. So the maze works until you get up to a point. Let me run this again and show you again. as you can see, the maze is going to get stuck. You get stuck in this corner here. And it's still looping here. So no matter where you go, it's just going to keep getting stuck. Yep, as you can see, doesn't work. So, what we need to do is use this stack we created earlier. Now this is only going to take like a couple lines of code. So, let me see, when we insert this, oh, we're done. When we insert this, where am I? When we get to the next cell, we want to insert it into the stack. So, table insert, stack, and the current one. Yep, okay. So if next cell, if there's neighbors, then it will do all that, and it will insert it into the stack. Else if the stack is greater than 0, then. So if there's if there's unvisited cells left that haven't, been turned into a maze yet, it's going to run here. So if the number of stacks is greater than 0, then stack the number of stack. So that's basically the very last item in the stack. Dot base. We're gonna basically make this red. So dot base, dot brick color. I'm gonna make mine red. Equals whatever. So I'm gonna make it really red, so you can actually see it. And we're gonna set the current to, or basically the last one in the stack. But we're also gonna remove it from the stack at the same time. So stack, number of stack. The number of stack, this here basically means, so the stack array, but the last one in the array. Because the number of stack is the number of items in the array. So let's see what happens when we run this. Okay. As you can see, it's not working. So, we debug this. There's no errors, at least. I guess that's a bad thing, isn't it? But I don't want to print the neighbors anymore. Okay, so I fixed the maze. So the problem was this check neighbors part. So I'm comparing it to the top one right now, and I was almost right, pretty much. So I changed this line to this. So let me tell you the differences here. And oh, I see what I've done here. I forgot to check. I basically forgot to check an extra value on the X ones when I did them up here. So sorry about that. This is what it's meant to look like. So just pause the video here and copy this out. And when you fix these, I believe it's just these two that needed to be fixed. But when you write out those two, run the game with the stack, as you can see, when it goes red, that's basically meaning it got stuck and it's going back over itself. And as you can see, it ends up at the end. So if I increase the size here, so basically tripling it, should take a little longer to set up. Yep. And as you can see, the maze is working completely by itself, and it's going to be completely random every single time. And you could set an endpoint and figure out a way to get over here if you want that to be in the endpoint or something, I don't know. well, yeah, you can watch this super satisfying effect.